All right, we have data in our environment, and now I want to run a couple of tests. These are single sample t-tests. We're going to run two different kinds, a single sample means test and a single sample proportions test. With both of them, you need a target value, and with the second one, you have to do most of the calculations, I say by hand, but we're going to do them in R. But there are two things that R can't calculate that you need to calculate. So for the first one, I'm going to have a target value. So my target value on this one, just going to put it in here so we can see it. And this is all as a comment because we're not running any code here. In 1980, the mean number of kids people had, mean kids was 2.03. And I want to check and see if Americans in 2010 were having the same number of kids. So to do this is a very simple t-test. So it's just t-test, then we have to pick our variable. So this is going to be from the GSS 2010. The variable is childs. And then, and here's the key, you just put in your target value. So this is the population parameter we're comparing against. That's called mu. So we put mu in and equal to 2.03. What that code is going to do is tell Rstudio and R here, I want you to do a comparison using the mean value and the standard deviation and everything else we'd need for that variable sample size. For the 2010 child's variable, compare that to the 1980 mean, which we've given it, 2.03. And when we run this, we should get in our output down here a t-value. So that is our test statistic right there. They can be positive or negative. If R didn't calculate a precise p-value, we would compare that to the critical value for a t-distribution given the sample size and degrees of freedom. Our degrees of freedom are quite large, so in this case, if it was 1 or 2-tailed, it would vary, but we can just do that comparison, or we can look at the p-value. Here, it's showing what our p-value is, which is less than our typical alpha, which is 0.05. Which means we can say that we're 95% confident that the number of kids Americans were having in 2010 is lower than it was in 1980. And then we would give our best estimate for how many kids people were having in 2010, and that would be 1.885. So the average number of kids has actually declined over time. So that's our first one. Our second one is going to be a proportions test. So this is a single sample proportions test, and for this one, again, I've given a target value that I pulled out of the GSS as well. In 1980, about 60.5% of Americans were married. We need to see if that's still true or was still true in 2010. So you can't do this the same way as up here because now we're not dealing with a mean. We're kind of treating the proportion of Americans who were married in 2010 and in 1980 as a pseudo-mean, but it's a proportion. So we're actually going to treat that as a proportion. All calculations for this are done as proportions, so always calculate as proportions, which means this is really 0.605, 605, 605. Okay, so what we need is a couple of things here. I'm going to load the EXPSS library. If you don't have this, of course, install packages, EXPSS. This is going to allow me to check a couple of things about that variable, assuming you have variable labels in your data set. So I'm going to first check the variable label. The variable here is marital, and that's going to tell me basically what the question is asking. The second part is the response options. So that's a value label, VAL lab. And that's going to tell me my options, which I need because I'm only looking at one of these groups, right? So there's married, widowed, divorced, separated, and never married individuals, plus those who are missing. What I'm interested in are the married individuals, and I need the proportion of that. So the easiest way to get the proportion of married individuals in the data set is to do a prop table of a table. So this is going to convert a table into a proportions table for our variable of interest. This is marital. And right there is the proportion of Americans who are married in 2010, which is 0.436. That's the proportion that we're looking at. Proportion married in 2010. So we want to compare those. Now, obviously, we can already see there's a difference. The proportion has gone down, but to do the actual calculation, we need two numbers. We need a standard error of proportions, and then we're going to do our test statistic. So we'll calculate our test statistic, which we'll do here in a second. To get our standard error of proportions, we actually have to do the square root of P sub s, the proportion of our success category. So P sub s in this case is going to be this value right here, 0.436, multiplied by everybody else. I always like to do this as 1 minus P sub s, so that is everybody else. And then that is going to be divided by n, but we don't have n yet. So I'm going to go back up and just do one other thing. To get n, I'm going to just table that variable. It's the easiest way to get this. So those are the people in each of those groups. I'm just going to add them all together in the numerator of this formula. And that will give me my n. So this is P sub s multiplied by Q sub s, which is everybody else, divided by the sample size. And I have to take the square root of that, and that is going to give me my standard error of proportions. So this is also S sub P sub S, S PS, it's fine, is equal to 0.01097. So that's the first step. That's telling me my standard error of proportions. The next step is to calculate the test statistic. The test statistic is P sub S minus P sub mu, the proportion in our population, which is the value that I gave, the 0.605. So to get our test statistic, we're going to do, as my numerator, 0.436 minus 0.605, so that's my numerator, divided by this value right here, S sub P sub S, 0.01097. That will give me my test statistic, right? So we're going to run that, and it's big, right? So my test statistic in this case, test statistic equals negative 15.405. We would compare that to critical values from a t-distribution table. That is going to be based on your alpha, so your cutoff, typically a 95% or an alpha of 0.05, and your sample size. Our sample size is big enough at this point that I can confidently say my critical value is going to be 1.96. I always like to use absolute values, so I would compare the absolute value of my test statistic, 15.4056 versus 1.96, whichever is bigger, again, absolute values. Then if mine is bigger, my test statistic, my p-value is smaller than that critical value. So in this case, I can say my p-value is less than 0.05. I don't need to know the precise p-value. I just need to know whether it's less than my cutoff, which means there is a statistically significant difference in the proportion of people who were married in 2010 versus 1980. And then, of course, you should give your best estimate. So in 1980, 60.5% of Americans were married. That has clearly gone down. And as of 2010, it was 43.6% of Americans who were married. And we are 95% confident that that difference has changed, and it's a statistically significant difference.